Well, welcome everybody. I want to thank everybody for joining today. This is our next Build Your Simulation IQ webinar. Today we're going to be talking about the NACA0012 2D airfoil model for Simulation CFD. I'm really looking forward to share these results with everybody, and as well as thank the validation team within Autodesk for helping out with running a lot of these models. So this is actually our 9th webinar for the CFD series, and in my mind this is kind of the end of at least really looking at turbulence models and external airflow, and we'll be starting to go into some other different modeling techniques starting in November, where we're probably going to be doing a smoke modeling webinar. So that should be pretty exciting. Those are some really neat models that you can run. For those that are joining for the first time, you can always find more information about all the different simulation webinars within our forums. And for those that get direct emails, it's probably where you learned about this event as well. Just for your reference, if you follow the link that's in the bottom of this slide, so autodesk.box.com/CFD9, that will actually take you to a shared folder that you can download this presentation, as well as a share file for one of the models that we have run. So you're going to have fun with that and enjoy. Just remember, this recording will eventually be posted to YouTube within the Autodesk Sim 360 channel and the Build Your Simulation IQ playlist. And you'll find all sorts of different recordings there from all the different products within Autodesk Simulation. Every month we post to the forum a bunch of different articles that we write based on the cases that we solve within product support. And when you download this presentation, you can follow the links and read about the articles themselves. One I just want to point out that does come up on occasion that I like to just add a little note on is, the question of why is Simulation CFD not using all the available RAM? And the simple answer to that is because the solver is tuned to use the RAM that it needs. So you can't allocate more RAM and have that solve your analyses any faster than it already is. If you need your analyses to solve faster, then really it comes down to upgrading your CPU or having more cores or things of that nature. So for today, it's a very simple presentation in some regards. We're going to start off with inspiration. Why the NACA0012? Then we'll be going into what our NACA Airfoil is for those that aren't familiar. That'll be fairly brief. Then we'll go into the 0012 itself and test data that's available out there, especially the ones that we're comparing to within our validation effort. And then lastly, I'll share the entire progress we have now with all of our data points, as well as show some sensitivity studies that I did in the background in terms of you change the setting, what does that do? Things of that nature. So really, I want to thank Wolfgang Fischer for making this post. It really gave me the opportunity really to spend some time with looking at this model. And what his post really came down to was that lift was about 15% off and drag was ridiculously off in all intents and purposes. And the quote that really kind of stuck out to me is this really the best we can expect? And no. There was definitely some things we could adjust, but unfortunately those adjustments were not obvious for Wolfgang, or really anybody, except for people within our team. So from there, we'll start diving into NACA Airfoils themselves. So NACA Airfoils date back to the National Advisory Committee for Aeronautics, basically a predecessor to NASA. And one of the things they did is they created a whole code system to define different airfoil shapes. And the airfoil shapes that we'll really be focusing on today are the ones that start with 00 in the front, which basically means that they're symmetric airfoils with a number afterwards. Okay? And that just defines the half thickness to the airfoil. So there's different equations and codes that define different types of airfoils that have camber and so forth. But really, for us, for this modeling, we're really sticking with the NACA0012. So at this point, when you're trying to validate any sort of airfoil, the first thing you have to do is draw it. But keep in mind that these airfoils, just as you see on the right-hand side, this is actually a Cessna, one of their models, And this actually is a NACA0012 airfoil, to my knowledge. So this is something that's been used for years successfully, and it's a great model to have fun with within CFD. So in terms of modeling airfoils inside of Inventor, just as an example, and I use Inventor, of course, because that's what we have here, but you can do very similar modeling techniques within any sort of CAD package. But one thing that I found very cool inside of Inventor that I wanted to share with everybody that actually has it available to them is that, outside of developing your airfoil inside of 2D, there's actually something within the iLogic functionality that you can actually create a form that you can then use to, on the fly, change your parametric models. Right here I'm just changing my angle of attack, and of course with all the parametric values that I can then use to drive my refinement regions, in essence, that I have around the actual airfoil on the inside. Okay? And you can have fun with this. You can program it to switch to different airfoil shapes. You probably can't really see that unless I zoom in. As well as, in terms of when you think back to, if you're familiar with any airfoils or tried to have done airfoil design in the past, you've probably designed it with a trailing tip to the airfoil. And one thing that does to the actual model is that when you switch to the trailing tip, it has the slightest reduction in the angle on the backhand side. And that is due to a closure problem with how the NACA equations are actually formed. And with this sort of model, we decided to retain the true equations that are used, but include a small round to the back end to close off the actual airfoil itself. This actually works to some of the meshing strategies more to Simulation CFD's strength, and I can show that when we actually start getting to the model. Within the NACA airfoil itself, when you actually look at the sketch for this model, you can actually drive your sketch shape right within Inventor within a 2D equation, and just literally type in the equation I showed previously within the PowerPoint. From here, you can, of course, drive some tables, and then you can launch that into CFD with having multiple designs using the iParts and iLogic. For instance, here I have multiple angles of attack that I can switch right to and leverage for quick automation. Okay. So I'm just kind of curious for everybody that's out there right now. Have you ever actually tried to actually validate an airfoil before? We've kind of taken the moment to sort of talk about what airfoils are. It's a pretty simple topic, and then going into modeling that inside of CAD. And right now, if I were to close this poll and share that with you, you'll see that really no one has been successful. And I'm not too surprised, and we'll go into that within our tool, at least if that's where you tried to do it. A few have actually tried, but most people have never tried. So this is really more of an interest to them. So that's cool. I'll hide this. Okay. So at this point, we have a model. We can start playing around with it inside of CFD, but really, if you're looking at validating towards some sort of experimental data, let's get some good data. So I'm going to present two different data sets that we are using to compare our CFD results. The first one actually dates back to some NASA Langley testing back in 1988 that was looking at purely just the NACA0012 airfoil for all sorts of different operating conditions and angles of attack. And I listed some of their summary findings. And one thing that is interesting with this result is they looked at what is considered tripped versus untripped data. And all that really means is that in the leading 5% of the airfoil, they in essence applied sandpaper of different roughness, in this case 60 and 80 grit, right to that tip. And that basically creates an extra layer of turbulence to that leading edge. Otherwise, with this airfoil, you get purely laminar flow on the leading edge, and this way you're going to get turbulence throughout the entire airfoil. Okay. And even within their test data, they actually did not really get good comparisons to their theory back then, unless they were actually comparing to those tripped results. So I found that pretty interesting myself. The next set of data was actually from Sandia Labs in 1981. This actually was looking at multiple different airfoils, more for actually using for wind turbine applications, vertical axis wind turbines. So one of the airfoils they looked at, of course, was the NACA0012 because it's one of the common airfoils that people look at. So in this case, they looked at a wide-ranging list or value for Reynolds number and looked at a full rotation of angle of attack, all the way from 0 to 180 degrees. And you get lift and drag, moment values, and so forth from these results. So when you actually end up plotting this test data, okay, so you have the Sandia and the Langley Labs results. We have 4 different plots. We have 2 for smooth and then 2 for the Latson results for 60 grit and 80 grit. And there's a few things I want you to realize is that the lift, especially at lower angles of attack, really jive very well with or without any sort of leading edge tripped testing. But as we start adding extra angles of attack, the data starts spreading for the lift, and eventually we end up getting a little extra lift before stall when we start looking at angles of attack around 15, 16 degrees and so forth. Afterwards, things start getting a much larger spread, a little more uncertainty. With the drag, there's a very noticeable, actually nearly 100% difference between the smooth results, which is going to be that lower trend down here on the right, versus the tripped results, which is a little bit higher. There's actually a fairly noticeable divergence between the 60 and 80 grit results. I found it interesting that the smooth results actually seem to converge together at higher angles of attacks to the very lower grit compared to the higher grit. Okay. A couple of things that kind of lead into the next slide is also notice that the Shadal smooth data, it almost seems like it peaks or minimizes right at the 2 degrees, while the Latson really sort of plateaus from -2 to 2. All that comes together in a paper that was looked at in 1987 from NASA Ames, where it actually looked at results from, I think it was about 40 different wind tunnels, comparing, what their strategies were for testing, the quality of the results, how good were all these different tests. So when you start looking at drag, you see 2 different trends, and as you probably guess, breaks down to tripped versus untripped. And then the lift really has one primary trend. But even within all of these different tests, experimental tests, it's quite a large range of values. So it's sort of a teaser. Within this plot, how does CFD really match into these trends, Simulation CFD at Autodesk, at least at 0 angles of attack? Right about there. Okay, so to me, quite right in reason with all the other wind tunnel experiments in terms of 0 angles of attack. Okay. So what is our strategy going to be within trying to model the NACA0012 for our means here? Of course, we're going to have an airfoil. We're going to be using a 1 meter cord. The tail of the airfoil itself is going to be that rounded geometry instead of a fixed tip. So our angles on the backhand side fit the airfoil equations perfectly. The wind coming at the airfoil itself, we're going to be using that a Reynolds number of 1.76 e to the 6, which is about 0.08 Mach, so this is well within incompressible ranges. And this is air at standard temperature and pressure. We're going to vary our angle from -4 all the way up to 20 degrees. So we're going to capture our stall condition as well as just look a little bit at the reverse rotation of the airfoil. Then we start talking about actual setup changes within Simulation CFD. For the most part, we're going to be following our standard advanced turbulence technique that I discussed a few months ago, with some slight changes. Okay, so as I even talked about back then, it's a starting point, and then from there, really, as you always do with CFD, root it back down in some test data. We're always looking to reduce testing, not eliminate. So within the advanced turbulence, if you actually did notice the forum post, I mentioned two flags: the use SST RC and the SST new IWF. We'll enable those. You'll also use the updated wall calculator. This was released a couple releases ago, and this is a newer form of the boundary force calculation that is considered more accurate, especially for wall forces. Then for meshing, what we actually did for the validation runs was we used 60 enhancement layers, which seems like a ridiculous number, but we'll look at what 30 and 15 also look like in terms of results. And then we have a fairly thick mesh enhancement. So those next two settings is actually, they go together to define your total thickness. Okay, so if you have a layer factor of 0.84 and a mesh enhanced thick flag set at 400, basically it's 400% of that layer factor value. So you're growing it by 4x. Then we applied a surface mesh or edge mesh really of 2.5 millimeters, and that grew double to the next surface, and then grew and grew and grew to expand outwards from there. So why use the flag use _ SST _ RC? This flag is considered a curvature correction factor applied to the SST K-omega turbulence model. And we originally applied it because we were looking at what's called the Coanda effect, which is the tendency for fluid to be attracted to nearby surfaces. So if we can sort of fall on the left-hand side, and this is from a NASA Langley paper, from the 3 images on the left, you can see how the fluid going over the backside of an airfoil has a tendency to sort of tear away from that actual airfoil. And if you look at with and without SST, the fluid actually has a tendency to stick to that airfoil all the way and then start kind of pulling around to the backside, or sort of flow forward, in other words, on the airfoil. Once you actually include this curvature correction term, the fluid then tears away or separates from the airfoil sooner, and that's what we're showing on the right-hand side is our simulation CFD results with that curvature correction. So if you look at the image kind of in the bottom center, and then the larger image on the right, and then also looking back at the recirculation region, this is really what the flag is capturing very well now. That eye is very well defined. So it may not really affect the results all that much, but it is an airfoil, and especially at higher angles of attack, this might capture some recirculation region. So we use that flag. And that flag also goes together very well with our SST Underscore new Underscore IWF flag. So this actually implements what's called a slip wall formulation. So basically, if you were to look at how the solver is solving for the wall itself, there actually is a velocity at the wall, okay? And that's by design. When you look at the results inside of Simulation CFD, we're actually applying a zero velocity at the wall just so it looks right. Otherwise, it would look sort of strange when you looked at your iso surfaces or your planes and so forth. But this is considered to be a more accurate method for solving for pressures and velocities, and I find it very interesting. There is a slip wall formulation for K epsilon as well, and we did talk about that during the turbulence model webinar a couple months ago. So those kind of go together. So using both these together was what was really needed to get good results. So without these flags turned on, Wolfgang would have been fighting for a very long time with the software to get good results. So at this point, what are the preliminary results? I've taken this long to build up to it, and this is our current preliminary results. And I say preliminary because I think there's still more we can do to change what the trend looks like at higher angles of attack, either having more mesh, or maybe now that we have these very large wake structures, potentially we need to start looking at the oscillations and so forth. Okay. So as you can see here, the lift looks phenomenal in my opinion, all the way up to, when we look at the 80 grit, it seems to stall right around 15 degrees, and then it tapers off from there. So we're really capturing that peak lift fairly well. The drag, as I noted before, fits the tripped results very well as well. And this has to do with the SST turbulence model. If you look at the forum post, actually, Omkar made the comment about how the SST mega turbulence model is basically a always-on turbulence. It doesn't have a laminar state where it can really solve for 100% laminar, where if you could, then you could actually approximate those smooth results, that bottom trend, much more accurately. Okay. So those are the results, and I think at this point, Wolfgang can go back and really start fitting those results in, and really looking at different airfoil designs for whatever project really was. Now, the question is going to come up, well, great, you had all these settings. What if I didn't use 60 layers? What if I used the limit within the UI of 15, by the way, as a flag, of course, to basically extend beyond the UI limitation of 15 layers? What if I use 15? What if I change my layer thickness and have half of it instead of the entire value? So this 400%, for instance, would be our default. So let's change mesh, mock, solver controls, and convergence, and see what happens. And I think for many of these results, it won't be too surprising. Some of them are actually very interesting, in my opinion. So I ran those results out within a small sensitivity study looking at 10 degrees only. And let's first look at the plot on the left. When you look at all these blue dots down here, these are all the different runs that I did. And these two values up here are considering using our default. When I say default, it means basically the setup that we use for the entire validation sweep. And all I did was either A, turn off the SST flags that we used, or I only switched from ADV5 to ADV2. So this really shows the sensitivity to advection for especially the drag coefficient and its accuracy. So that's why ADV5 is definitely considered more accurate compared to ADV2. Now SST, I'm actually very surprised how sensitive it really is. And talking with our developers, they're looking in to see if there's something that can be changed within the SST model itself to improve its results. Now when we start looking down to all the other results, this is where I find it much more interesting. Okay, so this is somewhat confusing to look at because I did put them all on the same plot, but let's look at the legend and work from top down. Of course, we have all of our different test data. Here's this Shadal down here with this kind of green circle, and then all of the other test data, the Ladson, is all within the yellow, square, triangle, and diamond. Okay. So even with all the changes that we did, it's really not too bad in terms of clustering of the results around the actual test data that we have. Now within meshing, we changed a couple of things. We changed the number of layers, as well as, if you look back in the previous slide later, we also changed the layer factor, so the total thickness of the mesh enhancement for the 15-layer run. Okay, so if we look at the three dots pointed with 15, this is going to be a little bit thicker. This is actually the 15-layer run itself, and then this is going to be the 15-layer. I'm sorry, this is going to be the 15-layer, very thick, This is going to be 15 layer very skinny, and this one's going to be our default run with 15 layers. So even when we look at 15 layers with all the default runs, it really doesn't change results drastically, still within reason. But when we start adding in more layers, okay, so here's our 15 value right here. This one right here, that is actually our 30. And then this big cluster of a whole bunch of different points is actually where our 60 is. So 30 actually probably would have been reasonable, but 60 is where we eventually settled on. Okay. Within meshing as well, we looked at adding more and less mesh. So our default 100% is in this cluster. And then I took the size that we had, 2.5 millimeters, and took a value 75% of that, so more mesh. And then I did less mesh. So potentially, as we add more mesh, maybe the results do start drifting this way. Maybe the fully mesh-independent results are over here. But you know what? It's still within reason. It's still within just a few percentage or within the data points that we have within test data. So have we gone far enough? Probably. Probably with an error of all the other 40 different wind tunnel test data that we already have. Okay. From there, I just went from Mach 0.08 to Mach 0.15. This is reaching more of the limit of incompressible assumptions as the air accelerates around the airfoil. Still within reason. It actually ends up being almost exactly the same as the Shadal run when you look at the drag and lift values. From there, I did a bunch of solver changes. I turned intelligent solution control on and off. I turned on and off the auto startup routine, if that's something that people have ever looked at. There's on and off and extended and so forth. So I just turned that off, for instance. None of those changes changed the results at all. Basically went right back to the exact same result. The only solver change that really did anything was going back to the advection results, where that actually did have a profound change in the trending. Okay. Convergence. This is the one that I found most interesting myself. When we talk about convergence, you're thinking of that window with the auto convergence assessment tool within Simulation CFD. And it starts off with default. You know where default is? If you look in that previous graph on the left-hand side, it's off the plot. It is just way, way out. It's not anywhere close to convergence. Okay. When we look at tight, it starts to get pretty close. It's probably pretty reasonable place to run your model out, but it really is not fully converged yet. So what we did is you can turn off the range slider with the auto convergence, and I'll show this in a moment, and you can start adding manual extra orders of magnitude to the different convergence term. So what happens here is I add an extra order to those terms, and then an extra 2 orders and an extra 3 orders. So what you learn here is that, at least for this model, adding in 1 or 2 extra orders of magnitude and waiting for auto convergence, that is where it really starts getting close to being fully converged. Otherwise, you're left with the option of basically turning off auto convergence and over-solving a problem, which is usually what I end up doing, then setting something for like 10,000 iterations and letting it run for a day or so. Okay, so those are my different adjustments that I made. If we went back up to these results, this sort of summarizes what I did again. So this was the key for Wolfgang. He needed these flags. He was already using AWF. He was already playing around with solution control off and on a startup. You can basically ignore those. Having these off, all that will really do is potentially allow your solution to converge faster. Sometimes it really won't do much of effect at all. Okay. And at this point, are there any questions that have been coming in? Because I'm going to go into the actual simulation CFD results themselves. So I'm just curious at this point. I mentioned the poll question that Wolfgang posted. Who actually saw this for people that joined? Yeah, what was the question? Okay, so there was a question that came in from Dan about the angles of attack, and has that really changed the best settings found? And what we really tried to do when we ran these models is we kept those settings. We kept them meshing. You know, we had to move our refinement regions that we put in at like the tail of the airfoil, make sure that actually tracked the airfoil. But otherwise, we haven't gone into what happens when we add more mesh to something. And that kind of goes against what you try to do with validation. You don't want to keep changing your settings. I think when you look at the trends of our results, it fits very well until we reach a stall condition where there's a lot more turbulence in the model. So I think when you start getting to that past stall condition, we might require more mesh. We might require maybe to run transient to be even accurate because of weight conditions that could start forming. It's not really steady anymore. But otherwise, no. The simple answer, not really. Okay, so in terms of that poll I just asked, let's close that and share those results. And about 60% of people actually did see that poll or that forum post, so that I find that interesting. And that means most people were excited probably that we're going to do this sort of content. So let's go into CFD. Probably tired of PowerPoint at this point. I am. Yeah, so this is our model, okay? Working our way out. You can see a very coarse mesh throughout most of the domain. We have a refinement region on the right-hand side that kind of captures the wake that as you start. You don't see it? Oh, sorry about that, everybody. Okay, so you can see now going into Simulation CFD. In terms of the meshing strategy, if there's no gradients, you don't really need a whole lot of mesh. So as you work your way out, you're going to have a very coarse mesh throughout most of the domain. And then as you can probably see, there's a little bit of a refinement region. Looks like a target, and then you start getting another refinement region, another and another. The tail or the wake of the airfoil, we have a refinement region going down to allow that to go all the way to the outlet. There actually is two of them, one that kind of ends here, and another one that ends right about there to allow that to transition. And we keep coming in. And for the most part, there's a mesh assignment here, a mesh assignment here. And eventually we get in all the way to the airfoil. And at this point, you can really start to see the mesh enhancement and how that is formed around the airfoil itself. Okay. And this is actually the 15-layer run I did. So all of these are for the 10-degree angle of attack model. Okay. In terms of the model setup, let's kind of look at this a little bit. With airfoils like this, you almost always start setting up the mesh at the surface of the airfoil. You're going to start in, you're going to select these edges, or if you're doing a full 3D run, of course, the surface itself, and you're going to start defining a mesh distribution, because this is really going to define how you grow outwards. So of course we have a value of some nominal value, in this case 2.5 millimeters. And then from here, you'll start defining your surface growth, in this case twice the size, and then growing outwards from there. Okay, and that's what all these different refinement regions are that you can easily define within any CAD package that you like. Okay, going outwards. Now, within any model like this, there's going to be certain areas where you're going to want to add in a little more mesh. And that's where having mesh refinement regions come in handy. And most of these you can be designed fairly intelligently, so you don't have to reapply them or move them from one CAD change to another, or angle of attack versus another. But one that we really that really has to follow the tail is the refinement region down here. This is to make sure that as the air leaves the airfoil on the backhand side with nice crisp velocity profile. Okay, so it's just a box and we apply a value in there. And really this size was the same size that we had, actually a little bit smaller, half the size of the actual airfoil shape. Okay. Boundary conditions for this type of model are super simple compared to a massive electronics model. For instance, you have velocity coming in the inside. Typically you put slips on the top and bottom, and a pressure on the backhand side. Sometimes, even though you're running steady state, you can still apply, or it can make sense to apply an initial condition. So in this case, we actually apply a velocity condition to the entire air domain, just to completely start the air moving. It just saves a few iterations in the long run when you're running many, many different jobs like this. Solver controls, of course, you can have solution control turned on or off. In this case, it was off because that's how we ran all of our runs, ADB5. When you start thinking about having solution control turned on and enabling auto convergence, when I talked about adding extra orders of magnitude, all that meant was switching from default to tight, take that number, switch to edit individually, and literally just add an extra order of magnitude here. And that's it. And if you add another one, you add extra zeros and then switch this to 7. Okay. I wouldn't probably bother much beyond 1 or 2 orders of magnitude within your models. If you actually look at the number of iterations it took to solve each one of those runs, there's some notes in here. I thought I made a note in there. Either way, it went from about 2,000 iterations for default to 5 for the ADV1, or the extra order of magnitude, or sorry, 5 for the tight, and then 1 order of magnitude went to 7 or 6 or 7, and then 2 went to 8 or 9,000, and then when you went to 3 orders of magnitude, it actually went beyond 10,000 iterations. I had to continue the run once it actually hit that. So that's why I say 1 to 2 orders of magnitude should be more than enough. Okay. In terms of flags, this might scare you for a moment. So these are the 2 flags that are really required to run the model and get good drag values. This I apply just to make sure that I remember to put ADV5 on, because of course we want to have that on. This mesh boundary layer blend flag adds a little bit more resolution from the wall mesh into the core of the mesh. This, of course, is the residual boundary force flag to get more accurate wall force calculations. And these 2 allow you to adjust some of the mesh enhancement beyond what the UI controls allow you to do. So you want more layers, you can use this flag. You can type in any value you want. And this mesh enhancement flag is a % value applied to the UI value for layer factor. Okay. From here, you can start really seeing all the different runs that we did. And I just set all these up. I ran it on the cloud, and the next day they were all done. And then what I used was a new tool that we recently released that I helped write, which is called the Design Study Loader. And this is available on the App Store. And what this really does is once, everyone runs into those days where you run a lot of models and you need to load them all. And what do you have to do? You have to sit here, you have to double click each one of these runs. You got to wait for it to process, and you really can't do anything. The model's locked up, and you got to sit there and keep it going. This tool, all that really allows you to do is, there's 2 buttons. You can sort of see what the current status is. All these right now, they're idle and the results are loaded, so there's nothing really going on. But if results were actually unloaded and it was idle, you could click on this Load Results button, and it will automate the process of opening up the first one, second one, third one. This one's still running, potentially. It'll skip it over and go to the next one and automate that entire process for you. So it really does save you some time. So I leverage that quite a lot with this tool. Okay. So any other questions that are coming in? I encourage you throughout the entire presentation, by the way, to type in questions that you might have.
There's no questions that I can see, Royce. Pretty quiet today.
maybe 11 o'clock on the Pacific Coast wasn't a good time for energy. So let's go back to the results. One thing that typically comes up when people are talking about external aero is the placement of the enhancement layer or the number of layers as well. So one thing to look at here is what does it look like when you actually switch to 60 to 30 to 15 layers. And all I'm really leveraging here is our decision center. And of course, when we start adding more and more layers, you can really see how the density of that mesh, mostly near the wall, due to the gradation factor, is really just squeezing more and more layers right on the inside. It doesn't really change the outer layers much at all in its resolution. Okay. Now, in terms of trying to assess, is this layer thick enough? Is it thin enough? Is this close enough to the wall, and so forth? In terms of close enough for that first layer, all you're really looking at there is, of course, your Y plus value. And this Y plus value, let's get rid of that. Of course, since these layers are so skinny, you really got to zoom in really far. When you're talking about a Y plus for SST, you really want to eventually start approaching a Y plus value of 0.3 or less, especially when you're trying to look at validation for lift and drag. That's where it's really designed to get below. So 0.3. So this 15 layer, we're upwards around a value of 4. So that's why with this specific layer factor, why going from 15 to 30 is most appropriate. From 30 to 60, if we jump right to the 60 model, for instance, whoop, didn't want that. Shoot, there we go. And we start looking at our Y plus value. First off, you notice right in the max value within the turbulent Y plus range, our worst case here is 0.02 basically, much, much less than the 0.3. So we know within our 60 layer, we're more than resolving our subviscous boundary layer within the flow profile. So that's good. So we're resolving that inner constraint. The outer constraint, though, is less defined. How do you really assess how thick this layer needs to be? Because it does do a better job to capture that boundary layer. And if you look at an XY plot of multiple runs and look at what that boundary layer looks like, you can see right away, this is our sharp gradient. That's why we need all those mesh element points coming right in the early portion away from the wall. And eventually we start getting to this linear portion of growth, once we get through the initial hump of the boundary layer. Okay, and right here, this is actually where you see a transition from our nice structured boundary mesh to our actual TET mesh. Okay, so what we want to make sure is that we are somewhere in this more linear portion of the boundary layer. Okay, so if you were to actually look at an XY plot and this transition looks like it's backwards down here, you probably need to make your layers thicker so you capture this trend. As well as, when we start looking at some of the results, you can switch to some of the turbulent terms, potentially. For instance, like maybe eddy viscosity. So eddy viscosity, of course, or effective viscosity, sorry. So effective viscosity is basically the modified viscosity value as altered by the turbulence model. So basically, if there's turbulence, then viscosity, the effective viscosity, is going to change. Okay. On the backhand side, the mesh becomes coarser, so there's a lot more diffusion going on in the results, and this is why it's spreading outwards. So if anything, if you were to talk about changing these results, I might actually add a bit more mesh on this wake side, but it probably won't change the results all that much. Okay. But when we start coming in and looking at our flow profile, you can really see how the development of our boundary layer kind of looks like that. Okay? So especially in this leading edge where you want to really capture the pressure coefficients going around the airfoil shape as well, you probably want your mesh enhancement, to be about this thick. Okay. From there, the mesh enhancement elements to the core elements, there's structural differences, but really the equations that are being solved are exactly the same. So as long as you have a clean transition from your wall elements all the way into your external flow, then that's what you really need to make sure you do. And from there, that's where the solver takes over. Okay, so in terms of turbulence, it's more critical that you get the mesh close to the wall as possible to capture the nonlinear portion of the boundary layer. And from there, it's really just controlling the transition to get an appropriate mesh. Okay? Any questions out there? Okay.
Not so far, Royce, no.
Okay. I'm going to take this opportunity then while people think about some questions. As you may have noticed, we do a lot of these webinars within all the simulation products, and we're also growing to include AutoCAD. We're including all sorts of other different products in the future. And I'm just kind of curious, because I'm part of the team that helps organize these, is what kind of resonates more with you in terms of what these are called? You may not even care, but I do. And, does the name Autodesk Help Webinars mean more to you, or Autodesk Help Live? If you were to read something, one of those two, what would capture your attention more? What would make more sense to what I'm doing right now? Awesome. I appreciate that. And just so you know, there's a resounding agreement on Autodesk Help Webinars, and that was where my mind was at as well. So I appreciate that. Okay, so I think there was a question that came in, John. Is that right?
Yeah, that's true, although I've asked Vlad for a little bit more specificity. His question was, how can I apply this to internal flow?
So I'm going to ask Vlad to define what kind of internal flow. Are we talking about valves? Are we talking about electronics models? It's a very open-ended question.
Okay.
I need a little guidance here.
There's a little more. It's probably enough. So he says, and he's still typing.
Heat exchangers. Yes, heat exchangers. So
and
really
also
with
the
heat exchangers.
comment above, can you see that? So he has some turbulence generators in a channel of a triangular shape.
Yep, so that's all, Vlad.
Okay.
Going for all of those. So we're looking at heat exchangers. If you're not looking at pressure drop, okay, let's say you have a defined mass flow rate on the two parts of your heat exchanger, and you're really trying to look at the heat exchanging performance from the hot and cold side, for instance, then this does apply a little bit. But since if you're not looking at pressure drop, you can get away with a little less mesh because you can have less boundary layers. Maybe 5 to 10 when you're leveraging the SST, especially when you're looking at liquid-based heat exchangers. Okay, and that'll be much more accurate. Now, if you're starting to look at pressure drops, this is relevant. But what I would actually have you do in that case is leverage probably the 1 or 2 cycles of the mesh adaptation and let that really resolve some of the complex meshing that you would need along the actual shapes of your triangles of your heat exchanger. Okay, so that's probably what I would do, but I would still probably leverage about 5 to 10 layers of mesh enhancement when it comes to SST, K, and Mega. If your heat exchanger is actually all gas-based of some sort, then you can actually just go back and use K epsilon with probably 3 to 5 layers of mesh enhancement and do pretty good at that point. Okay. It's about the optimization of the air inside the heat exchanger. Optimization of the air fin inside the heat exchanger. Yeah, so I'll stick with that comment. Now, one thing to think about, so there's a lot of things you can learn from this webinar. You can learn about, well, okay, what would it take to model external flow around some sort of shape? Okay, check. We sort of talked about that a lot. Another thing you can take away from is for heat exchangers, sometimes you need to think about convergence, and did you really allow your model to fully converge, especially when it comes if you're looking at the pressure drop to the system, because the thermal performance, that will converge fairly easily. You can start using what you learned about convergence criteria and doing a manual adjustment and really think about, when you look at the convergence plot, is it really done? Okay. Some other things you can think about within this is, well, when you start looking at the shapes inside of your heat exchanger, what is really going on? We have some sort of liquid going over the shapes, and depending on the channels around these shapes, I don't know what it looks like. Maybe what you really need is more mesh within the root, so that you make sure that you really allow the flow to travel through the different shapes to get a good mesh or a good result. Vlad, does that help you out? Hopefully. It's much easier when I see something. Okay, great. If you want to talk more about that, definitely reach out to us in support or through the forums. If there's a picture you can share, that usually helps out a lot. Okay, so we have about 5 more minutes. I went over a lot today, and a lot of it is more of a sharing and trying to close the loop on what I thought to be a very interesting forum post, and provide some guidance to Wolfgang and share that with the community. Okay. So in that case, it is about 5 minutes before the top of the hour. I want to thank everybody for joining today. And if there's any sort of topic around this that you want to bring up, I please welcome you to go to the forum and post any extra questions. You're more than welcome to download the PowerPoint presentation, as well as I posted the 15-layer run, basically this one right here, to the box folder that I shared. So you're welcome to download that and run that within 2015 and hack away at it. If you have any questions on that, that is a great one to post to the forum, since that will be publicly shared. Otherwise, next month we will be continuing our discussions within smoke modeling and go from there. So everybody have a great day.